the webinar of today that will be held by Professor Kyle Rollins on liquefaction and lateral spread. Kyle Rollins received his degree from Brigham Young University and his PhD from University of California at Berkeley. After working as a geotechnical consultant, he joined the civil engineering faculty at BYU in 1987, following after his father, who was previously a geotechnical professor. His research has involved geotechnical earthquake engineering, deep foundation performance, bridge abutment behavior, collapsible soils, and soil improvement technique. He has supervised more than 130 graduate students and published over 190 papers. His work typically involves full-scale testing to evaluate and improve performance of bridges and buildings. The American Society of Civil Engineers has recognized his work with the Haber Research Award, the Wellington Prize, and the Wallace Hayward Baker Award. In 2009, he was the Cross-Canada Geotechnical Lecturer for the Canadian Geotechnical Society. More recently, he received the Utah Governor's Medal for Science and Technology and the Jory Ostenberg Award from the Deep Foundation Institute. Actually, Professor Kyle Rollins is a visiting professor at University of Chieti, and so we are very glad that he can have this webinar that is the first of two webinars that we are organizing during the month of June. The webinar is organized in three parts, so we can interrupt the presentation at the end of each section for a short question, and then for other question we can have time at the end of the webinar. So Kyle, if you want to share your screen and webcam, we cannot see you. Okay, thank you.
All right, let's see if we can do this. All right. All right, are you seeing that?
Yes, we can see. We can see.
Okay, it's a pleasure for me to be here with you today and to tell you, talk to you a little bit about liquefaction assessment and liquefaction consequences. This is work we've been doing over the last 20 years or so, and more recently with gravel liquefaction. And I'm pleased to be here at University of Chieti Pescara and look forward to the opportunities we'll have together. This is a photograph of my university at Brigham Young in Utah. It's one of the largest private universities in the United States. It's sponsored by the Church of Jesus Christ or Latter-day Saints. We have about 32,000 students. And earthquake engineering is a very important topic to us because those beautiful mountains that you see in the background are a result of normal faulting. So about 80% of our population lives within 20 kilometers of this Wasatch Fault. So we want to know all we can about earthquake shaking. My university is located in the state of Utah, where the Winter Olympics were held in 2002. Probably more of you are familiar with California. We're a couple states in the Rocky Mountains. We have 5 national parks in Utah with really amazing natural arches and geologic formations that you should visit sometime if you can. BYU is about 9,300 kilometers from Ud'A, so it might seem like we're a long ways apart, but if you have the right perspective, then you'll be able to see that we're next door neighbors. And you have probably learned over the last year, like I have, that the world is getting smaller every day. And with the new technology we have, we can interact with each other very closely, even though we might live around the world. So I'm using this perspective to think about each of you as my friends and colleagues. Turns out I come from a line of geotechnical engineers. This is my father, Ralph Rollins. He performed investigations for about 5,000 structures and 90 dams when he was alive. And since he was a professor, I got to take soil mechanics and foundation engineering from him. And this for me was a real pleasure. I don't know if you would like having a class from your father or not, but I really enjoyed this. This is my daughter, Rachel Rollins, and she was a civil engineering student at BYU. And again, I don't know whether she enjoyed it or not, but she took soil mechanics and foundation engineering from her father as well. So I've written a paper with my father, and I've written a paper with my daughter. And this is my granddaughter, Ella, who's showing some early interest in soil behavior, and we hope that keeps up. Let's talk now about liquefaction. Sarah told me that there might be some who are new to this topic, and so I wanted to give a little background. Liquefaction normally occurs in loose saturated sands, like you see up here, where this is saturated void space. And when the earthquake starts to shake the ground and shear stresses are induced, there's a tendency for those sand particles to consolidate, and this increases the pressure in the water. And eventually the pressure in the water can equal the vertical effective stress and lead to a condition of liquefaction. Sometimes it's easier to show liquefaction than it is to let's see. So I wanted to show that to illustrate the effects of liquefaction for those who might be new to this. It's a rare opportunity to see this happening in real time. One of the leaders in our field was H. Bolton Seed, or Harry Seed, and he originated the techniques for liquefaction assessment with simple methods that could be used by regular engineers to assess liquefaction. And his approach was to use case histories to identify sites where liquefaction had occurred and plot them in terms of the cyclic stress ratio versus the blow count, and take open points where no liquefaction had occurred and draw boundary lines. And these are defined as the triggering curves that decide whether liquefaction would be triggered for a given blow count. In class, Harry Seed used to say, get the facts first, the theory can come later, then you'll have something to base the theory on. So he didn't try to fit the facts to the theory, he did it the other way around. And this is a tradition that lives on in the United States with the Geoengineering Extreme Events Reconnaissance Team, where we receive money from the National Science Foundation to investigate after important seismic and landslide and hurricane events. So I was part of the team that went to Chile after the 8.8 magnitude earthquake there, and the part of the first team that went to Tohoku after they decided it was safe enough with the radiation that was being emitted from the damaged reactor. Here I am with Steve Kramer and Josef Aschash as part of that study. So these post-earthquake investigations are really critical for us to learn how things really work in the world. Liquefaction can induce a number of problems. It can cause a loss of bearing strength, which results in settlement of our structures. It can cause flow failures. It can cause lateral spreading. So when we talk about bearing capacity failure, a building may be perfectly stable on the soil in its static condition, whereas after an earthquake, when the soil liquefies, the building can tip and settle. And here's the classic picture from Ud'A, Japan, where many of these buildings tipped and fell over. Some of the other buildings did not tip, and that is because they have deep basements that gave the building much more stability. The other buildings have shallow foundations. This is what you might call a geotechnical failure, but a structural success story, because even the building windows weren't damaged and people could walk up and get their belongings and bring it back down. Is this something that happens only in Japan? No, certainly not. We have a number of case histories now where similar events have happened. Another case where not even the windows are damaged, but the whole building has settled and tilted in Turkey. Here's another building in Turkey. And in Japan, after the Tohoku earthquake, there were a number of cases where the sand boils were observed, and you can see that some of these buildings are tilted 1 to 2 degrees. We can have flow failures where a slope that was stable before the earthquake slides after liquefaction. So here's a flow slide in Half Moon Bay in California after the 1906 San Francisco earthquake. And this didn't cause much damage to anyone, so it was just something of interest. But if this happens under a major earth dam like the lower San Fernando Dam, which was damaged in this earthquake in 1971, then it can be a major problem. The upstream slope slid into the reservoir, and there was only about a meter of soil left to prevent overtopping of this dam, which would have resulted in flooding of over 100,000 people downstream. One of Harry Seed's triumphs was reconstructing the cross-section of lower San Fernando Dam based on the final failure surface and identifying these zones in blue where the soil had liquefied, piecing them back together and then identifying the area which had liquefied. And as a result of this case history, we now have techniques for predicting performance of dams and earthquakes. A third problem is lateral spreading. Before the earthquake, this potentially liquefiable soil might exist below a clay layer that's non-liquefiable. After the earthquake, the sand can liquefy and these top layers of clay can float along on top of the underlying soil towards a free face or towards a river. Of course, this can cause major damage to port facilities like this one in Roko Island, where the damage for the lateral spreading pulled apart the crane towers, and this led to $11.8 billion of damage to the port. Only 6 of 187 berths were usable after the earthquake, which is a significant economic and long-term economic damage to the city. We saw similar things at the port of Coronel after the Chilean earthquake in 2010, where this conventional pier was damaged to the point that it could not be used. And you can see the surface of the asphalt as a result of lateral spread. Many of the containers fell off of one another. We went in and measured the displacement. There had been about a little over a meter of displacement at the edge of the port. And it went back to about 0 displacement within 20 meters. Sometimes we have piles that are located in sloping ground, and it becomes an issue of what kind of resistance these lateral piles might have against the lateral movement of the ground. Of course, we can have significant damage to these reinforced concrete walls, or piles like this in the Niigata, Japan earthquake. This is a bridge in Costa Rica that we investigated after a major earthquake in 1991, where the lateral spreading pushed the bridge deck into the river and caused a loss of about 19 bridges along the coastline of Costa Rica. Here's damage to piles at the port of Coronel in Chile. This pile, we wondered if it was a battered pile, but no, it had been driven vertically, and the movement of the ground in this direction had caused the pile to move about a meter in one direction. I have Dominic Asamaki here for scale, and you can see that the ground has moved about half an Asamaki. As a result of that, we had buckling of the cross beam here on one side, compression failure, and tension failure on the other side. My structural engineering friends tell me that's exactly what we want it to do, absorb all that energy and still remain stable after the earthquake. Well, how can we investigate this liquefaction phenomenon? We can do so with small-scale testing, with centrifuge models, maybe 1/50th of the size of the soil. We can do so with laminar shear boxes, where these are shaken and these little segments of steel boxes can move like they would in an earthquake. But more frequently, we would like to see things at large scale and how the earth really performs. As we mentioned previously, post-earthquake investigations are always very desirable, but in many cases, you don't have all the information you would like to have to better understand how the bridge really performed, particularly if it had collapsed. You can use a vibro-sized truck to shake the ground and cause liquefaction. This has been very helpful to work in New Zealand. Or you can use controlled blasting, which is what we have tried. No method is perfect. Each tells us a little bit of the entire story, so it's useful to investigate from all these techniques. But with blast liquefaction, there are a number of advantages. First, it tests at large scale. It can test the native soil in situ with real microstructure and aging. You can liquefy large volumes at one time, so you can investigate the performance of an entire system. You can liquefy to maybe 10 or 14, maybe even 20 meters. And we have seen that we have settlement similar to that that's induced in a real earthquake setting. But there are some problems. The mechanism of pore pressure generation is not exactly the same. And so we need more research to calibrate this to earthquake conditions. We also must avoid damage and vibration to adjacent structures and people, and this is a much more expensive thing to do. Gabriel D'Annunzio, this university is named after, as I understand it, once said, I cannot understand why the poets of our day complain of having come into the world too late or too early. I believe that every man or woman of intellect can create his own beautiful fable of life. And I have to agree with him. I think we have the opportunity to use our creativity to try new techniques and investigate in new ways that can advance society. He also said, everything was attempted. What was not done, I dreamed, or I dreamt. So when we first proposed this idea for blast-induced liquefaction, one of my colleagues called it the mad scientist dream, where we would set off an array of explosive charges to liquefy sand and observe the performance in situ at full scale. So our plan was to set off small explosive charges, 1 to 3 kilograms, and liquefy a zone of soil, in this case about 5 meters thick. And we'd have non-liquefied soil below that, and then we could test the foundations inside this liquefied mass. So the first opportunity we had to do this was at Treasure Island liquefaction. In the Treasure Island liquefaction test, you can see Treasure Island, which is a man-made island in San Francisco Bay. Here's San Francisco, and here's the Golden Gate Bridge. And since that time, we've done tests like this at a number of sites around the world. So our dream has become kind of a reality here. Our approach was to first experiment to see what it took to cause liquefaction, prior to putting the foundation elements in, we liquefied the ground using these explosives and measured with piezometers to see that we really did liquefy the soil. Here's we always use licensed blasters to do this work. This is Butch mixing the nitromethane and ammonium nitrate and putting it into the hole. And this was our first test. So this should look similar to what we saw at Tohoku in a natural earthquake, where there were liquefaction features, these sand boils or sand volcanoes as a result of the testing. And from this testing, we were able to investigate the lateral resistance of a pile, first for a single pile, and then for a group of piles. Subsequently, we had the opportunity to do this test in Charleston, South Carolina, for this new bridge that was being constructed, a cable-stayed bridge, one of the largest in the United States. And the designers of the bridge wanted us to investigate how the foundations would perform in this situation. So one of the problems with the previous testing was that it was under static conditions, and we wanted to load it dynamically. So we used this statnamic load sled, rocket sled, where we detonate fuel pellets, and they expand and have gases that move out in one direction, and that causes the sled to move in one direction and the foundation to move in the other direction. So here's this sled being put into place on a little runway. It weighs about 100 tons. It's put into position in the combustion chamber. This is about 2.5 meters in diameter. Then this was fired off. And just so you can see what that looks like, I'll show this video. It's about 7,000 kilometers. So there's opportunities for doing this. This has been done by a number of researchers, including my colleagues in Japan. They told me once, Kyle, your baby has grown up. They had a very huge, hundreds of charges going off to investigate a variety of ground improvement techniques. It's also been used in Christchurch, New Zealand, and we'll talk more about this in a couple weeks' time at the second webinar. So blast liquefaction testing does provide a very useful method for evaluating pile and ground improvement at in situ at large scale. It has the potential for liquefying large volumes and to great depth, and we can induce settlement and pore pressures that is similar to that from an earthquake. It turns out I also have come from an academic family tree. Carl Terzaghi was the major advisor for my professor, Harry C. And of course, we all know Carl Terzaghi is the father of soil mechanics. And we can recognize Harry Bolton Seed as the father of geotechnical engineering. I haven't lived up to the full potential at this stage, but I can call myself the father of Rebecca, Rachel, and Chelsea, my 3 daughters, and maybe at some point the father of blast-induced liquefaction. Questions at this stage?
So Kyle, it's the end of the first part.
That's right.
Okay, so if there is any quick question we can have now, or otherwise we can go on to the next section. Okay, I think you can go on, Kyle.
Okay, I might mention that we've done several of these blast-induced liquefaction studies with Professor Amoroso and Professor Tony and Gottardi at University of Bologna, and it's been a pleasure working here in Italy on these kinds of studies. I'm going to talk now on liquefaction evaluation in gravelly soils using a new tool called the dynamic cone penetrometer test and also shear wave velocity tests. My co-authors on this study are Les Yaud, you might know as an expert in lateral spreading, and my graduate student Jashad Roy, and another graduate student named Michael Talbot, who works with the U.S. Bureau of Reclamation. This research has been sponsored by the U.S. Geological Survey, the U.S. Bureau of Reclamation, who's responsible for the design of and maintenance of dams in the United States, and the National Science Foundation. One question you might ask is, can gravel really liquefy? We know that in most cases, the soil that's most likely to liquefy is in this blue range, which is mostly sand. And we don't really expect gravel to liquefy. But and based on some early numerical analysis, we have suggested that if the permeability is greater than about 0.004 meters per second, pore pressures will dissipate as rapidly as they develop. So let's take a look at the grain size distributions of case histories where gravels have liquefied. And we find out, looking at these charts here, that there's a very wide range of gravels that have liquefied. But in most of the cases, even when we have 50% or more gravel, the sand content is typically 30% or more. So if you use an empirical equation like the Cozzini-Carmen equation to estimate the permeability of soil at case histories where gravels have liquefied, you'll find out fairly quickly that almost all these sites have permeabilities that are less than that boundary. And once you get about 30%, the soil permeability or hydraulic conductivity, is about the same as that for the sand. So even in cases where the soil might classify as gravel, it might behave as the sand in terms of drainage. Now, there'll also be cases where gravel permeability is impeded by a surface layer, and this surface layer could consist of clay or silt, or it could even consist of a thick layer of concrete, for example, at a port facility. And this is a photo of an excavation in China where they typically have 4 meters of clay overlying a gravel profile with fairly large gravel particles. So we might say danger, loose gravel. This is a highway sign I saw in Alaska when we were doing some studies there. But there's now a growing set of case histories, even some in the last year or two in Croatia and Albania, something like 22 earthquakes in the last 100 years where gravel liquefaction has been reported. So it's not just an imaginary thing, it's something that is happening routinely in every major earthquake. And two of those major earthquakes are in Italy, in Messina, the Messina earthquake in 1908, and the Friuli earthquake in 1976. So if we look at gravel liquefaction sites around the world, there's a growing number where people have identified gravels that have liquefied and done studies to quantify what's happening. This becomes a major issue for older dams because many times they were built on profiles that contained liquefiable gravel, but gravel wasn't supposed to liquefy at the time these dams were built. And now it becomes a multi-million-dollar decision to decide if there is a liquefaction hazard, and if so, how that soil should be treated to prevent liquefaction in the event of an earthquake. One of the techniques that's been developed in the United States is the Becker penetration test. We have found that the standard penetration test and the cone penetration test can provide unreliable results in gravelly soils because the particle size is large compared to the size of the sampler. So this BPT test was developed in Canada in the late 1950s to help address this issue. And the diameter of the pipe is about 16.7 centimeters. It's driven into the ground in 3-meter long intervals in a double core barrel with a diesel hammer. So it's like a small pile driving hammer, and it's going to measure the blows per foot, which we call N sub BC, from the bounce chamber pressure. Now, what has been done to utilize the Becker penetration test is to develop, and this was in sand, a correlation between the SPT blow count and the corrected Becker blow count. So if you had a blow count of 40 from the Becker penetrometer, you could then determine what the SPT blow count would be to use in your analysis. So then you could come to your favorite model for liquefaction triggering and determine the cyclic stress ratio which would cause liquefaction. One of the problems with this technique is that it has a straight-sided pile, and the result of that is that you can have friction on the side of the pile, which will reduce the amount of energy that's transferred into the pile or into the Becker penetrometer and artificially increase the blow counts. So Jason de Jong has come up with an innovative technique to measure the force that's transmitted to the bottom of the Becker penetrometer and has developed a new correlation between the penetration resistance at the bottom and the SPT blow count. But you can notice here that there's a significant scatter in the data. So if this is the best fit line, we have an error, potential error of plus or minus 40%. This increases the uncertainty about our prediction for cases where we really like to eliminate as much error as possible. So some of the limitations of Becker penetration testing is that there's a high cost to mobilize it to a site in the United States, and the testing costs are often high enough that we can only use this for major projects, not routine testing at all. As I've discussed, there's some uncertainty with correction factors for the Becker penetration test, and there's uncertainty with the correlation between the blow count for the Becker and the blow count of our equivalent sand. Probably the biggest problem with this method is that it's only available in North America, so most of the world doesn't have access to a test like this that could be used in critical cases, even in critical cases. So what we're looking at, one technique is the Chinese dynamic cone penetrometer. It's capable of penetrating loose to medium dense gravels. It's relatively fast, it's simple, and it's economical, so it can be used for routine projects that you might encounter any day of the week. And the most important advantage, I think, is that the triggering curves are directly based on field performance, just like all our other curves are. When we use SPT or CPT, we have a direct correlation based on case histories with that test. And we're trying to do the same thing with the DPT. The Chinese approach is to use a tripod, lift a 120 kilogram weight to a height of 1 meter, and then let it free fall. The cone is 74 millimeters in diameter. It tapers backwards to a smaller diameter drill rod, so there will be less friction between the soil and the rod and make it a more reliable test. So this is about 2.5 times the energy of the SPT test. So you have more energy and a larger penetrometer and less skin friction. The cone is driven continuously in the ground. You don't get a sample, but you do get, like with a conventional cone penetrometer, you get a continuous reading of the blow count versus depth. We record the number of blows every 10 centimeter and then multiply by 3 to get the equivalent value at 30 centimeters of penetration. We do have a correction factor for overburden pressure, but there's no consideration of fines content at the present time, and all the tests that we've done have fines contents less than about 30%. This test was first used for liquefaction assessment by the Chinese after the 7.9 Wenchuan earthquake in 2008. When they started to investigate sites, even sites that had what it looked like was sand ejected at the top, they discovered that the sites were largely sandy gravel. And they started the work of investigating 118 gravel liquefaction sites in the Chengdu Plain. Here you can see some of the ejecta. You can see sand and gravel particles, some maybe a centimeter or 2 in diameter, some even larger. These are core samples from a borehole next to a DPT sounding, and the DPT was able to penetrate through these materials. So even with 40 to 80% gravel, which is typical there, they were able to get through this. Here's one case history, a lateral spread at Banqiao School. They had 20 centimeters of differential settlement here and had to demolish the school and start again. There were lateral spread displacements of about 1 meter towards this canal or channelized river. Now, as the penetrometer goes through the gravel profile, it might hit a gravel particle and have a temporary increase in resistance. And as it pushes the gravel aside, there might be a drop. And so you can maybe make an estimate of the matrix blow count, and in this case would be about 10. So this would be the layer that liquefied and is used for developing the triggering curves. These are the triggering curves that were originally developed by Tsao and others. This was based on 19 sites that liquefied and 27 sites that did not liquefy. The red dots are the liquefied soil and the open dots are no liquefaction. And then these were probabilistic triggering curves values, 85, 70, 50, 30, and 15%. Many cases people use 15% or 30% for this triggering value. But you can see there's a large amount of uncertainty here because there's a very limited amount of data. One of my colleagues, Les Yaud, went to China and recorded the amount of energy that was being transferred into the drill rods as a result of this free fall triggering system, and found that on average they have about 90% energy transfer using a pile driving analyzer. And even in some cases they get low counts that are energies that are higher than 100%. And what was happening was the hammer was going higher than a meter before dropping as they were pulling it up very rapidly. So that's the standard we're comparing against. Now, if we compare the triggering curve for the dynamic cone penetrometer, the DPT, with that for the CPT, we can see that there is a lot more variability in the boundary of the liquefaction zone for this newly established approach in comparison with this approach that has hundreds of data points in comparison to this that only has about 45. So we would like to get to the point where we could have a much more certainty about the boundary between liquefaction and no liquefaction. We also want to look at triggering in terms of shear wave velocity. The advantage of this is it may not require a borehole if you are doing MASW testing, but there is some uncertainty with this approach. One of the other questions would be, are the curves for sand appropriate for gravel? Or do we need to adjust the curves to have a new triggering curve? So here's the typical triggering curve for sand with shear wave velocity of about 200 from Anderson-Stokey. More recent results from KN et al. Show a boundary of about 240 meters per second for sand. And if we look at the data that I just showed you from China, they're getting data that is now has about value at about 270 if you use the median, or maybe even 290. So there's a big difference between these sand curves and the gravel curves based on what we know to this point. We also want to know if we can reduce the spread in the DPT triggering curves with additional data points. Will the factor of safety we get from the DPT be similar to that from our Becker penetrometer? And can we use a less hammer energy to do this? So again, this shows some of the gravel liquefaction sites around the world. We, in our grant, expected to only be able to do some testing at the Bora Peak, Idaho test sites near Utah. This would be Whiskey Springs, Larder Ranch, and Pence Ranch. Gravel liquefaction sites in the Bora Peak earthquake, which is a 6.9 event, took place along this Lost River fault. And the sites we have are Pence Ranch with a 0.39 G, Whiskey Springs with a 0.5 G, and Larder Ranch at 0.5 G. Here you can see a photograph of Pence Ranch. There's lateral spreading here towards the river. There's about 3/4 of a meter of lateral displacement here between these fence posts that were initially side to side. And there was fissures with sand and gravel ejecta coming out. So we did 8 DPT holes here, 4 using the SPT energy and 4 using the hammer energy that the Chinese use. We did PDA measurements and we compared against 4 Becker penetrometer profiles that Ron Andrus had done. So here's a plot of this. At each one of these Becker holes, we did 2 DPTs with the different energy. In the United States, we have a rig built by CME, and it will allow us to switch from the SBT hammer to the DPT hammer relatively quickly in about 10 minutes, so we can do both tests. These plots show the BPT and DPT curves, blow counts after correction for energy effects in both cases. And as you look at those 2 curves, it looks like the blow counts are very similar, following the same kind of trends in both cases. This is a layer that liquefied, unit C, our worst layer. This was expected to have some liquefaction, some no liquefaction. And this was the zone that was not going to liquefy according to most predictions. And we had another site, very similar response. So what we did is did a liquefaction evaluation at the critical layers with the DPT and the BPT. At all the boreholes at Pence Ranch, for example, we have a factor of safety of about 0.35 with the BPT procedure and about 0.27 with the DPT procedure. So this is giving us some encouraging results. The 2 hammer energies are, after correction, are giving us similar blow counts. We went on to Larder Ranch. You can still see these large scarps where the ground slid down towards the river here. Again, with a PGA of 0.5 and lateral spread displacements of about 1 meter. Here's the cross section. We're seeing sliding going on through this liquefied layer here and into the spring. So this is our liquefied zone layer, which was maybe about 6 to 8 meters below the ground surface. And then the test Larder Ranch results here are showing the blow count versus depth. Again, we're getting very good agreement with the Becker penetrometer in both these cases. Here's our liquefiable layer. We measured the energy transfer at each of these sites at Larder Ranch so we could have an appropriate correction for energy. Here's the Becker penetration test, factor of safety in the critical layer of about 0.42, and with the this is with the DPT. This is the Becker. Here's the DPT, and a factor of safety of 0.29. So we're in the same general range of both of those cases. And then the last one is Whiskey Springs, photo by Lashiaud. This is, you can see this scarp moving towards the river here for several hundred meters. And they did some trenches across here to identify the zone that liquefied. They also had 2 Becker penetrometers and 4 DPTs with 2 different hammer energies that we conducted. Lateral spreading and going in this direction again, down the slope. And here again, you can see the scarps with the shear zone running through this liquefiable layer of gravel and then coming out at the base. Our BPT is giving us a factor of safety of 0.35, and our DPT is giving us a value of 0.46. So overall, for these 3 case histories, we're getting comparable factors of safety, not exactly the same, but similar from a much more simple test procedure. So at that point, we had finished what we were responsible to do for our contract, but we started to wonder, is it possible to work with colleagues and get tests done at other sites? And to my beyond my wildest dreams, we were able to get tests done at a number of sites in Alaska, Ecuador, Greece, Italy, Japan, China, and New Zealand. So here's a port at Manta Port of Ecuador in the Ecuador earthquake, 7.8 magnitude event. This is a pile-supported wharf. Going under the wharf, we could find after the earthquake that a lot of these piles were badly damaged. And when we looked at why that was, we could see that there was a large crack here. And our colleagues, Vera Javier Vera worked with us and did tests with the DPT at the port, and they found out that the zone that was causing the sliding and the lateral spreading here was a sandy gravel layer. So the sandy gravel had between 15 and 70% gravel sized particles, but with enough sand to still allow it to liquefy even without a bounding layer. Javier did 7 DPT soundings with energy measurements and also 7 V-sub-S profiles with MASW. And you can see here the zone that is liquefying is this zone from about 3 to 6 meters. We had the opportunity to go to Greece, to island of Cephalonia, where liquefaction had occurred at several ports, the Lizori port and Argostoli port. Here you can see lateral spreading that had occurred towards the face of the port. And the ejecta was both sand and gravel coming out of the fractures. So we used something like 7 locations at this Lizori port, 5 DPTs, with SBT hammer energy. We did PDA measurements. There were 2 where the gravel was much too large to penetrate, so we couldn't do those, even with our system. We had a track-mounted penetrometer, which was easily able to go everywhere we needed it to, and this PDA device. If you have to go to a site to do some work, Cephalonia Island is a great place to go, by the way. This is, again, the zone that was identified from the DPT testing, and we have a number of these points that are above the triggering curve, so they're where they should be. These are the average values in those ranges. Argostoli port did similar work. This is the liquefied layer and the averages, again, above the triggering curve that had been previously established. And our colleague, Demetrios Zekos, did MASW testing along the port with his student, John Hubler. And so we have this data as well. This shows a plot at the Lizori port, the Argostoli port. We had the opportunity to work with INGV and Professor Amoroso and Friuli to occupy sites where liquefaction had occurred and been reported by Sirovich after the 1976 earthquake. This is an alluvial fan deposit, and there were 3 events, 3 separate events where liquefaction had occurred. We had 3 sites that liquefied and 1 that did not, and we did DPT at 2 hammer energies there. Here you can see some of the gravel particles in the ejecta in this cornfield. A previous previous crossflow shear wave velocity test was available here. The grain size distribution curve showed that maybe 20 to 40% of the material was gravel sized. Here's the DPT testing taking place. Here's the instrumented rod to measure the energy transfer. And then we can identify this critical layer. And this was recently published, this paper in 2020 in the ASCE Geotechnical Journal. Here are our colleagues from INGV doing MASW testing of their data acquisition system and their sensor arrays. We found in many cases that the shear wave velocity was higher than what would be predicted to liquefy based on the sand triggering curves. So there's some adjustment that needs to be made here. Next site was Seward, Alaska. Our colleagues at the Department of Transportation there said, come ahead, we'll pay the money for the drill rig and you can test. This is a site that was badly damaged, where bridges were badly damaged in the 1964 Alaska earthquake with large lateral spreading. We did a number of DPT holes here. The nice thing about this is that it can operate very quickly. We did 8 DPT holes to about 15 meters in 2 days. We did PDA measurements. We had 2 hammer energies at each of 4 sites where the ground had failed due to lateral spreading, and we had some nearby cross-hole V sub S measurements. This is the liquefiable layer that can be identified here. We also decided to start using a cumulative blow count so that we could compare the blow counts from the SPT hammer, which is this one here in blue, and the DPT hammer, which was this in orange. And if we evaluate over a cumulative interval, rather than at each depth, we can see that we got very good agreement between the blow counts of the 2 cases. If you plot the light hammer blow count versus the heavy blow count, you'll find cases where there's an offset in the stratigraphy that causes confusion. And so we would recommend doing this kind of a approach to get the comparison rather than comparing at the same elevation. So we've looked at the critical layers from the DPT and from the shear wave velocity, which were quite evident. We also got authorization to do some testing at the Valdez, Alaska port, where there was a flow slide followed by lateral spreading. This is what the port looked like before the earthquake in 1964, and this is what it looked like after. Some 3 million cubic meters of material slid into the ocean. We went out to this site and did these DPT tests, where that just leading up to that site, where the major landslide occurred, with up to 7 to 8 meters of lateral spread displacements. So we were a little nervous, could this DPT really penetrate through these materials, these very large diameter river gravels? So we decided that we would try it, and here's the camera penetrating into the So that's an automatic hammer, and it operates very quickly and penetrated about a meter in something like 25 seconds. Then more recently, we had the opportunity to test at Wellington in New Zealand, where this center port was badly damaged by gravel liquefaction in the Kaikoura earthquake, where peak ground acceleration was 0.22 g. So this reclamation fill here is composed largely of dumped gravel material, and you can see that there's something on the order of 60 to 70% gravel-sized particles in that zone. and you can see the gravel ejecta. It's difficult to test at a port, so we worked with Misko Krubanovsky, and he helped us get access at the same sites where he was doing CPT testing. So these are our DPT sites, and they're situated at locations where liquefaction took place. So here's our DPT testing at the Wellington port. And we found out that at the end of the rainbow, there's actually a drill rig. We thought there would be gold or something, but it was a drill rig. So looking at the DPT profile at Wellington Port, this is our critical zone from about 4 to 6 meters. All the data points plot above the triggering curves that Sao et al. Had put together. But what we did find out afterwards is that there were also 2 other earthquake events where liquefaction did not take place, and they were poorly predicted by this set of triggering curves. So we needed to make some changes. It's very important to also have data from cases where no liquefaction took place. And so we also went to Valdez, Alaska, where a site where no liquefaction took place to get data to constrain the curves. And we came to L'Aquila, Italy, working again with Professor Amoroso and her students to find cases that did not liquefy. These are very important and critical to keep the curves from just wandering towards the right. So we did that, which turned out to be very helpful. And if any of you are aware of other sites where gravel, you know that an earthquake has occurred, but there's no indication of gravel liquefaction, we could use some more data to help these curves. So most of our data still comes from China, followed by US, New Zealand, Greece, and Italy. There are a variety of geological environments, from alluvial fans to glacial fluvial deposits in Alaska. We have a range of magnitudes. Most of the blow count, or most of the data is within 14 meters of the ground surface, which is very typical of liquefaction case histories. And these plots show the revised triggering curves. This is for the DPT. So here's our DPT blow count, and here's the cyclic stress ratio. All these solid data points are liquefied, and all the open points are sites where gravel did not. And you can see that these points, L'Aquila, were very influential in constraining the curve on the right, along with the data from Valdez, Alaska, where no liquefaction occurred to constrain them. So we now have 137 case histories. We're looking for more, of course. They're from 7 different countries, 10 earthquakes. This is a 200% increase in the number of data points that we originally had from China. And now, instead of just having data from 1 earthquake, we have them for 10 earthquakes. If we compare what we had previously, the probability of liquefaction curves are shifting upwards, particularly at low blow counts, and this was to match the results and the behavior that we had from Greece and New Zealand. So the case histories have made a change in what we're using now to analyze. At higher blow counts, the probability of liquefaction for 50% is about the same as what was on the original Sao curves, but the width of the triggering curves from 85% to 15% have narrowed substantially. So we have less uncertainty about where the boundary of liquefaction and no liquefaction needs to be. We also back analyzed using logistical statistical analysis to find a magnitude scaling factor for our regression equation. And for the gravel soils, it fits right here, which is very similar to the Idris and Boulanger magnitude scaling factor, a little higher than Seed's original scaling factor and a little lower than the lower bound from the Ud'A data. So the magnitude scaling factor from this test data plots about where we think it ought to be, even for the gravel soils. Likewise, we did new probabilistic triggering curves based on logistic analysis. We have a little more case history data, 162 case histories, again from 7 countries and 10 earthquakes. And now we're seeing a much tighter band on the liquefaction curves. So here are the changes in probability. The probabilistic V-best triggering curves are shown. You may be able to see, it's kind of confusing, but the dark curves are for the new curves, and the dashed lines are from the old curves, and that boundary between 85 and 15% probability is smaller, so we're refining the location and the boundary for liquefaction with the shear wave velocity. One other thing we did find out is that almost all the tests, when we put all the test data together, the boundary for liquefaction in gravelly soils is higher than the boundary that we have for sand. And so these new curves will help us get a better estimate of behavior of the gravel curves. So some of our preliminary conclusions, these are just being reviewed and approved by the ASCE Geotechnical Journal, is that once we use energy and magnitude corrections, the DPT yields liquefaction factor of safety that are reasonable, comparable to what we would get with the Becker test. The DPT and V-sub-S results were generally estimated fairly well with the curves that were there, but at small low counts and low V-sub-S values, we had to make adjustments to match what really happened in the field. We found that this DPT can penetrate gravelly soils even with the lower SPT hammer energy, but we recommend using the heavy hammer to reduce uncertainty in the correction for energy. Additional DPT and V-sub-S data is providing refined triggering curves, and we think this will be the case for another 5 or 10 years while we collect more data. And we think that this Chinese DPT, as it becomes adapted to practice in the West, has the potential to provide a simpler, more economical, and more direct method for evaluating liquefaction in gravels that could be very useful. Any questions about gravel liquefaction issues?
Sara, posso chiedere una cosa?
Sì, vai, Giuliano, prego.
Okay, thank you very much for the presentation. I have just some question about the correction for magnitude. You showed all curves related to magnitude 7.5. Of course, the Italian cases are related to much lower magnitude. Can you give us some detail on how you can take into account of this correction, please?
Yes, so that's a good question. In performing the logistical regression analysis, we use magnitude as an independent variable. So our variables are magnitude, CSR, the cyclic stress ratio, and the DPT blow count, and then independently got the magnitude scaling factor. What we did is for each magnitude, we plotted the correction factor for various blow counts once we'd done the regression, and we found that there was very little variation across a given blow count for various magnitudes, and so that would allow us then to make use an average scaling factor for each magnitude and produce that magnitude scaling factor. So basically we're using the magnitude as an independent variable like Rob Kahan did for the shear wave velocity triggering curve.
Okay, thank you very much.
Thank you. Other question? Okay, Kyle, we can move to the third section.
Okay, thank you. Okay, this third presentation is looking at lateral spread equations for large magnitude earthquakes. There are relatively few data points for cases where we have magnitude 8+ events. And this becomes a large issue for many countries where they have subduction zone earthquakes and want to use the lateral spread equations for predicting displacement of the ground in these large events. This is work that was done by my graduate students, Ginger Tryon, Nicole Williams, and my colleague Kevin Franke at Brigham Young, and Esteban Saez and Christian Ledesma at the Pontificia Universidad Católica de Chile, and we are grateful for their help. We worked on this together. They came to Utah and worked on this with us, and we went to Chile and worked with them. It was a very nice collaboration. We received grants from the U.S. National Science Foundation and the Chilean National Science Foundation to help with this study. So if we look at a block diagram showing lateral spreading, we might have this non-liquefied soil that's shown in brown, which floats or slides on a layer of liquefied soil that's shown in yellow. And that can produce sand boils at these cracks between blocks of soil. And the displacement between these blocks can lead to cracking and vertical offset between buildings and bridges and other infrastructure like pipelines and other things. So you can see on a roadway here that lateral spread has caused offset in this particular case. This is the bridge I was showing you from Costa Rica that was pushed into the river as a result of lateral spreading. These were the pile foundations that were damaged by lateral spreading in Niigata, Japan. And this is damage to the port in Ecuador due to a recent event that we talked about briefly. So in all these cases, we would like to estimate the displacement accurately so that we can determine if our structural elements can tolerate these movements. And if not, we may have to do some ground improvement, or we could potentially increase the strength of our structures, or potentially make our structures more flexible and able to adapt to the displacements that might occur. Lateral spreading prediction models can be divided into two general types. One are straight empirical models that use past experience or case histories to make displacement predictions. In contrast, semi-empirical model might use a combination of case histories and laboratory strain data to make predictions. So you may have a relationship between shear strain and relative density from your laboratory, and then you use that to correlate with displacement in the field case history. So there are at least 6 models that I'm aware of I don't know how much time we have to spend on all of these, but we've got maybe 20 minutes. I'm going to focus on the Bartlett and Youd and Zhang et al. Approaches in the empirical models, and Ferris, which was developed at UC Berkeley, and the Zhang, Robertson, and Brockman approach that Peter Robertson and his colleagues developed back in 2004. Bartlett and Youd developed their empirical equation at Brigham Young University, and here's some photos of Steve and Les Youd. Most of the earthquake magnitudes in the case histories that we look at are in the 6 to 7 range. There is one case history, the Alaska earthquake, that has a magnitude 9.2, but trying to base much of analysis on one case history is asking for trouble, I think. So most of the models have included this, but it's rather uncertain whether they are appropriate for this large range of magnitudes. And so the different researchers recommend different magnitude ranges. Of course, if we look at the ground motions for large magnitude earthquakes, in many respects, they are almost like having two earthquakes back to back, where we look at this one in Concepcion and one in Chile, and this one in Japan. The duration is about twice as long as some of the smaller magnitude 6 to 7 events that most of our methods are developed for. So you might imagine that there would be some additional displacement that would occur for a larger duration event. So our objectives were to develop some well-documented case histories of lateral spreading at 4 piers at the Port of Coronel in Chile from the Maule, Chile earthquake in 2010. We wanted to conduct liquefaction and lateral spread analyses to predict displacements at these sites and compare measured displacements for these large earthquakes with displacement predicted by available computer models. Then maybe make possible recommendations to improve the current methods when possible. So our lateral spread analysis procedures, I'm going to talk first about the Bartlett and Youd approach from 2002. It uses a number of variables. First, it uses 2 variables to identify the seismic inputs, the magnitude of the event, and the source to site distance are. Bartlett and Youd looked at a number of parameters like peak ground acceleration and spectral acceleration, other terms, but these 2 gave the best agreement with the empirical results. Now there's 3 parameters that come in this model that are based on the soil or the geotechnical properties. So one is the T15 value. This is the thickness of the layer in the slope with a blow count less than 15, and it doesn't matter in their model what the value is as long as it's less than 15. If you have a blow count greater than 15 and the whole profile has a blow count greater than 15, then there would be no lateral spread displacement. They also found that the fines content in the layer was very important. So as the fines content goes up, the potential for lateral spreading goes down, according to their model. And then they also found that the D50 size was important. So this became important for gravelly soils. So they used this D50 as the mean grain size within the T15 layer. Now, Les Youd wants me to tell you that you have to have, in order for this model to work, you have to have a consistent layer in the slope. You can't just test at one site and find a weak zone and assume that lateral spreading is going to occur throughout the entire slope. It is not going to work. So you need to find the parameters, consistent parameters for a layer of material. Then we have a third set of parameters. These are geometric parameters, so they depend on the slope and the offset. So S gives the slope of the curve, or y over x. If you have a gentle slope, less than maybe 3 to 5%, and then if you have a free face, say at the edge of a river, they recommend using the free face ratio, which is the height of the free face divided by the length to the point that you're computing displacement at. So Yao and others produced these regression equations, one for the free face and one for the gentle slope. And you can see that as the D50, as the T15 size increases, the displacement increases. As the free face ratio W goes up, the displacement goes up. As the fines content goes up, we have a decrease, and as the D50 size goes up, we have a decrease. So here's the comparison between the measured displacement and the computed displacement. So what do you think about this? Here's if everything was perfect, all the points would be on this line. But in reality, to bound most of the data, they have to have the measured be either twice or 1/2, so a factor of 2 on the computed value to get all the data into that range. So at first glance, you say that sounds very poor. We should be able to do better. Maybe the data is flawed, but I think you'll see in this presentation that this is very typical, and no matter what model you use, I think you're going to see this kind of variability. Now let's think about this for a minute as well. When we predict settlement under static, just vertical settlement of sand under static conditions, and we use the average value, what kind of variability would we see? In many cases, even for static conditions, you might still see plus or minus 50% from a prediction of static settlement. This is a far more complicated problem than that. You've got lateral displacements, liquefactions, phase transitions, and lateral sliding. So it may just be that that's about as good as we can do with an empirical model. Now, well, one thing that Youd found is that if we have a blow count greater than 15, then they had no lateral spreads that were observed in that case. So you ask, is this the absence of evidence of absence? In other words, does that mean that if we have a blow count higher than 15, we'll never see lateral spreading? Or is it just a case where we haven't seen it yet? Or is there a real physical basis for this? Well, if you look at the residual strength curves that were developed by Idris and Boulanger in 2007, I believe, they look at a curve where the soil is dilative, and where the soil starts to dilate and get strength and the pore pressures go down, we see a significant increase in residual shear strength. And it's right about this boundary of 15 to 16, 17. So this is suggesting that soil in an undrained condition is going to become very strong due to dilative effects at 15 or higher, and this could explain what's going on. Youd suggests that if you have a liquefiable layer in a slope, then you make this the height of the free face in the free face ratio. And he also suggests that you limit the zone that you are considering for liquefaction to a depth equal to h below the toe of the slope, and h is the height of the slope. And his argument, his contention is that if you have a pipeline or something below that boundary, that the potential for lateral spreading is very low, because the spread would occur above that zone and not cause damage to your pipeline. This needs to be tested with numerical models and more field case histories, but it's worked so far. One of the problems with the Youd method is the selection of the distance to the source for subduction zone fault. If we're working with a strike slip fault, we can easily get this distance and it will have some positive value. If we're using a subduction zone fault and our site is located here, then the R value that we're going to get is going to be 0 because we're already within the zone of surface rupture according to this joiner bore distance. So in this case, and we'll see the problems this causes, is that we're almost always at a 0 value. So when Youd and Bartlett used their method in Alaska, they went from the zone of significant surface energy release, which is from this distance right here, instead of going from instead of using this distance from the fault surface of the fault rupture, they used this distance to try and get a better fit with the behavior in the Alaska earthquake. To deal with this problem, Zhang et al. In 2012, this is different than the Robertson equation, replaced the magnitude and scale and distance factor with the spectral displacement 1/2 second period. This is based on a ground motion prediction equation for that region. Then they kept everything the same as the Youd formulation. The problem with this is now we have to have a calibration of a ground motion prediction equation for each particular region. Zhang was able to get a little better agreement, but not a lot more with his model, but it doesn't have that problem with the R value. Let's look quickly at some semi-empirical models. I'm running out of time, but Ferris model requires you to have the peak ground acceleration and the magnitude. So here again, we don't have to worry about the R distance. It uses the SPT blow count and then correlates with shear strain. That's the geotechnical parameter. And then for the geometric parameter, it uses the slope angle or the height divided by 0.25 times L max, which is the maximum length of failure. This correlation is based on maximum ground movement. So instead of giving you the displacement at different distances from the free face, it'll only give you one value. And it will, as a result, it's going to give larger values than Youd. Liquefaction assessment is based on the seated all approach, and it's supplemented by the Youd et al. So an example for Ferris would say if you have a blow count of say 14, you can come to this curve and get your strain potential index for a given cyclic ratio. And that would say that the maximum strain that you could have from laboratory testing is 15%. So for each layer within the liquefied zone, you'd find out this maximum strain potential. You'd multiply it by the thickness of that layer and get your damage potential index max. And then that would be used to calculate subsequently the maximum displacement with this empirical equation based on this dpi max and some slope properties. Here's her original database. Does this look familiar? It should. Again, it's if you look at the best, the predicted and measured 45-degree line, we're off by a factor of 2 in both directions. So trying harder, a little better, more refined seismic parameters, not much better estimate. So it eliminates the R term. It correlates with the physical shear strain. It doesn't, it considers layers with a blow count greater than 15. No limitation on depth, unlike Youd, and it only provides a maximum value. Zhang et al. Gives you peak ground acceleration and M sub W for the seismic parameters, correlation between cone tip resistance and shear strain for the geotechnical properties, and the slope angular free face ratio. Displacement is based on maximum ground displacement again. So he would use an adjustment that's based on Ishihara's work. So if he has a factor of safety of 0.5 against liquefaction and a D sub R of 50%, you get the maximum strain of 32%, 34%. Then again, like the Ferris model, you add those up to get an LDI max, and then use this empirical correlation for different slope geometries. And here's what he's getting for these different slope geometries. Look familiar? Once again, we're off by a factor of 2. This may be about as good as we can do with these empirical correlations. I'm going to skip quickly because I'm running low on time, but we looked at the Chilean earthquake, which had a very large rupture zone that you see here. And our site is lies directly above the rupture zone. In this port, the Port of Cornell, we have 4 piers that we are studied here, 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 and here. Okay. And it turns out that as you go further south, you get more shallow deposits and less lateral spreading. So here we have maximum of 2.8 meters of lateral spread, 1.5, 0.47, and 0. Okay, so it's kind of like a laboratory, a full-scale laboratory to see how our models do with 4 different case histories in our big sandbox. So as part of our work, we did site investigations at this La Roja Fisherman's Pier. So we have tests out in the ocean. We have CPT tests as close as we could get. Here, here, and here. And then we also have some CPT holes at each one of the other sites. We also have some on the pier itself that we're able to obtain. And this gives our displacements as we go down from each one of those sites. La Rojas has the lowest blow counts. The next one has a little higher. And you can see that as the displacements decrease, the blow counts also decrease. This shows a photo of the lateral spread at Las Rojas Pier. A lot of damage, disruption of the gravel or the concrete slab. Piles that were in this were pulled out of their cap. This slid ahead of the pier, so the ground is moving more than the structure. You can see that the structure is badly damaged. It's no longer a viable pier because of this ground movement. Again, 2.8 meters of displacement. We have a sand layer down to 10 meters and then clay. So this data is available for analysis. The seawater is about 3 meters. And so we're considering this zone, which has a cone resistance of about 5 megapascal and a blow count of about 6. This is the soil profile. So we're expecting lateral spread to take place in this zone right here in the clean sand, not in the clay. And this is the displacement profile as we go back from the wall. So we're looking at closer at this point. Here's the retaining wall at 2.85. This is back at that pile that was badly damaged from lateral spreading from this ground movement, where we have 14-degree rotation at the pile head and a displacement that is known at this level as well, which is about 0.5 meter. So the ground displacement of 1.5 to 2.25 meters is closer to the slope based on pile movement. So for each one of these, we also came up with the T15. We have a thicker zone at the north slope, 4 meters, that's less than 15, fines content of 11, D50 of 5, and W of 15 to 20. So this is the zone we're looking at. Again, it's this layer right here. The south pier only displaced 0.47 meters, relatively little offset. And in these cases, our cone tip resistance was 15 to 20 megapascals. And we had blow counts in almost all cases bigger than 15. We have one at about 16, and we still had some displacement here. So this is a very large earthquake. Youd had used the 15 as the limit for magnitude 7. So this is one case history that proves that it could have a little displacement, some displacement, if it's for bigger magnitude and longer duration events. So the south pier, we have a thinner T15, higher fines content, and lower D50, and that has led to less displacement. We looked at the displacement between the piers with some CPTs there. Here again, we have higher T values, so it correlates well between the piers. We also threw in some data from Tokyo Bay. Surprisingly, with all this filled material, we looked around and we could only find one case history where there was lateral spreading. Only one case history, despite this very large earthquake and what you would consider were soil susceptible to liquefaction. The distance from the rupture plane to Tokyo Bay is 110 kilometers. And the peak ground acceleration at that point was a 0.17 G. So this is the site where we have one lateral spread. It's right here. So we at these two locations, there's a seawall right there and a key wall here. This is a plot of it. You can see the lateral spread displacements, the offset of the seawall. And Yosef Hashash and I measured the displacement, lateral displacement as a function of distance behind the wall here, and that's our values, 1 to 2 meters. I was wondering why there's so little displacement, and it turns out that these fill materials have relatively high fines contents, 30 to 40% typically on average. And I think as a result of that, the lateral spread displacement that would be predicted with the Ud'A method predicts very low displacements. The critical zone here is shown at 3 to 4 meters. It's fairly thin, high low counts. So comparison, selection of the R value is very difficult. If you go out to the fault rupture, you would use 160 kilometers. Joiner and Bohr would say 0.5 kilometers to use in the mouth in the Ud'A and Bartlett and Ud'A approach. Maximum coastal uplift is at 47 kilometers. So we tried using the 0.5 kilometers, which is what Ud'A suggests, and we get unreasonably high values measured in comparison to what we actually got. So we're not getting close to this. And when we use the maximum uplift, we're on the other end of it, but we think this is unreasonable to use this approach. One thing that we did find that was interesting from the seismologist might be able to give us some better understanding about that is that based on the aftershocks, they found the location of the rupture surface, or these big asperities where a lot of the energy was being released, and the closest to our location was about 90 kilometers. And when we put 90 kilometers in, all our data plots in the right position. And if we do the same thing with Tohoku, where we're outside the shear zone, we get really pretty good agreement with what was measured. And looking at this versus distance, the agreement's not too good, but considering the uncertainty that's involved, it's not too crazy from what we would see, what we'd predict with what was measured. The Zhang method, we would hope that it would do better. It does all right with the case history and histories in Chile, but when we add the Alaska data, it is not giving us good values. And similarly, if we add the Tohoku data, it's outside the range of what's predicted. So it needs some work. The Ferris approach is giving us predicted values that are a little too high. It's just on that boundary. When we add Alaska in, it's okay, and Tohoku is predicted well. So the Ferris approach is not doing too badly. And then in our comparison with Zhang and Robertson, again, we're over-predicting the settlement, or over-predicting the displacements considerably relative to what was measured. And part of this is due to the non-conservatism of the approach. The Alaska and Tohoku earthquakes displacements are where they ought to be, right on. But it may be that we don't need to consider the full thickness of the layer, and we need to limit the thickness that is involved in lateral spreading. And so we use the Chetan approach to limit the depth that we're considering for displacements. And when we do that, even the Zhang, Robertson, Brockman gives values that are reasonable. So quick conclusion, regardless of the method that you use, I think you're going to have to deal with large variations in measured versus computed displacements. You might think, well, I'll use a numerical model that has a spring or a residual strength or a sliding block model. Steve Kramer has analyzed some case histories with this approach as well and found out that the variation is even larger for those sliding block models. We found that displacement is minimal with the blow counts greater than 16. So for magnitude 8, we would probably bump this boundary up to 16 or 17 to be a little more conservative. Fines content and plasticity really decrease lateral spread displacements. So if you have a model that's predicting large displacements, you need to factor in the fines content to get a better estimate of what's going to happen. The empirical models with the site to source term for R are unreliable with these large subduction events because you have to use a R of 0. The Zhang et al. Empirical model uses local attenuation relations and could potentially be a better approach. Both the semi-empirical models tend to overpredict the measured displacements, particularly for deep, loose cases, and that's a weakness of these models. We think they probably should limit the depth that's considered, and you could potentially do that with the Chetan et al. Depth reduction factor, especially for deep, loose sites. Well, we come to the end. I showed you the delicate arch. This is called Delicate Arch in Utah. It's about 25 meters tall. And I hope someday when COVID is over that some of you will visit me in Utah and you can go with me and we can see this beautiful arch that an engineer or a geologist ought to be able to really appreciate. Thank you for your time.
Thank you, Kyle. It was a very interesting webinar. I don't know if there is somebody for any question for any topic that Kyle showed to us.
May I make some little comment, Kyle?
Yes.
Thank you very much for the last for the seminar, but also for the last image you showed us. I was in Arches a long time ago, and I really remember it was a beautiful place, one of the best places I ever visited. Anyway, I was just thinking about the lateral spreading problem with very high magnitude. You know, from the seismological point of view, dealing with this high magnitude can be quite complicated because yes, the rupture zone can be 100 kilometers wide. So probably it's very complicated to find, some relationship because the rupture, how the rupture evolves on the fault zone can be very crucial, as you've shown. So I think it's a really a very, very hard topic to deal with. That's my opinion just from the seismological point of view. I think you agree with that.
Yes.
And yeah, that's all. I think that also the big ground acceleration tends to saturate for very, very high magnitude events. So doesn't increase the peak ground acceleration with magnitude linearly. So also this parameter can be quite tricky also because peak ground acceleration is quite an unstable parameter. So I think you need to work a lot to find a good correlation.
Yeah, I know Christian Ledesma down in Chile is working to try and find a solution. He hasn't found a perfect solution yet, but he's using different parameters that are energy bracketed terms and is having a little better success with that. So, but I agree with you. It may be kind of beyond our ability right now. So anytime we make a prediction about what's happening on these large subduction zones, we need to take a second thought about it.
Kyle, I have a question on the last part of your presentation that was very clear, talking about lateral spreading and all the options we have to measure this phenomenon. What do you think about which is the best in situ test to study lateral spreading? SPT, CPT? It looks like SPT has a more wider experience compared to CPT, that on the other side is the most common tool used for liquefaction.
Yes, this is a really good question, Sarah, because my first answer would be, oh, we should always use the CPT. It's a better test. It gives us more reliability. It gives us a continuous profile. But when we try and use the CPT to get the correlations, we don't see the improvement that we're expecting. And I think it has something to do with the corrections for fines contents to get an equivalent fines content. It's not a simple thing, and it depends on the potential for dilation and other factors. So I would say if you really that you would probably do a better job with SPT right at the moment, knowing what I know about some problems with the CPT correlations. I think you would probably do better with the SPT, but my suggestion would be to try and use more, do more tests instead of putting them 1.5 meters or apart or 2 meters. You might need to put them closer together to get a better understanding of the stratigraphy involved. We have a difficult time finding a Q sub C that will cause the settlement, the lateral spread to stop. Like we have a SPT value of 15, 16, or 17, but we don't have a good value of N of QC or QT that stops all of the displacement. This is kind of a surprise to me.
Okay, thanks, Kyle. We have another question from Madhusan.
Yeah. Very nice presentation, Professor Kyle. I have one question. We are all familiar with this SPT N60 for that energy correction. But the first part of your presentation, I joined a little late. I saw something like N120.
Ah, yes.
Can you please say what that?
So this is the number of blows to drive the dynamic cone penetrometer 30 centimeters into the ground using a 120 kilogram weight dropped from 1 meter height. And so to distinguish it from the typical SPT energy, we use this N120.
How about the efficiency of that? Do we really apply any energy corrections for that?
Yes, the standard for this is 90% efficiency, but we're not usually able to get that same efficiency in with an automatic hammer or rope and cat head hammer. So we have to measure the efficiency or measure the energy that's transferred with the hammer that we're using and correct it to a hammer that gives 90% efficiency like the Chinese standard. It's a very good question.
Thank you.
Thank you. Any other question or comments? Anna?
Hi, I have a question about the gravel section of the presentation.
Okay.
Usually in nature, you never have just purely gravels. You have gravels in a fine matrix. My question is, in your experience, the fines is going to play a role, or we can totally ignore the fines?
That's a really good question, one we don't have all the answers to yet. All the case histories in our database so far involve non-plastic fines with fines content typically less than 25 or 30%. We have some case histories where there is gravel in a matrix of clay, and we have considered those non-liquefiable. So we think if you have a plasticity index greater than maybe 10, or a high fines content, maybe 50% or more, that it's unlikely that it would be liquefiable, even though it has the majority of the particles might be gravel. We think if it's cohesive, it's unlikely to liquefy and have problems. But this is something that we still have a lot to learn about. So as you go through your practice and you find something, if you run across the site, we would love to collaborate with you and investigate this to see if it can add to our data set and help us resolve issues like you're talking about.
Thank you so much.
Thank you. Any other question or comments? Okay, so probably we go through the end, and Alessandro would like to say something to conclude the webinar.
Yes, Kyle, just to thank you again on the behalf of all the members of the board of our PhD school. So thank you again to be here for these seminars that are a good opportunity for our students. So thank you.
Thank you. Thanks, everyone.
Thanks, and see you for the next webinar on ground improvement on the 25th of June, same time. Okay.
Okay.
Bye bye.
Ciao, thank you very much. Ciao a tutti.
Ciao.
Bye.